So here is an example of a first-order system. y1 prime of t is 2y1 of t plus 1 bunch of y2 of t, and y2 prime of t is 1y1 of t plus 2y2 of t. What we are interested in is these two functions. We are going to let this solution vector x of t be composed of these two functions, y1 of t, y2 of t, and we know that this has to be of the form e to the lambda t. This is what we're going to try. So it leads to an eigenvalue problem for this matrix A. This system above can be written as 2, 1, 1, 2 into y1 and y2. And that means we have to study the eigenvalues and eigenvectors of this matrix here. So we're going to find the lambdas. What we need to do is take the determinant of this matrix, set it equal to 0. We'll have 2 minus lambda squared, subtract 1 is 0. 2 minus lambda squared is 1. If we were to take the root of both sides, we'd get the absolute value of 2 minus lambda is 1. So 2 minus lambda is plus or minus 1. And that's going to give me two different solutions. 2 minus lambda is 1. So that means lambda is 1. Or 2 minus lambda is negative 1. So that means lambda is 3. We now need to find the eigenvectors associated for each one of these lambdas. So if lambda is equal to 1, what we then need to do is solve a minus I equals 0. And remember, we're always looking for non-trivial solutions. So if we were to take our matrix, we'll have 2 minus 1, 1, 1, and 2 minus 1, and that's going to be augmented by the 0, 1, 1, 1, 1, 0, which we could then row reduce to 1, 1, 0, 0, 0, 0. C1 is equal to negative C2, and C2 is free. So in this first case, we will have C2, negative 1, positive 1. So what we're going to do, as is standard for eigenvector notation, is we're going to take this basis vector to be the actual eigenvector. The solution is the vector 1, negative 1, e to the 1 bunch of t, or e to the t. Now, at the same time, if I were to take lambda is equal to 3, what I then need to do is solve the system a minus 3iv is 0, 2 minus 3, 1, 1, 2 minus 3 augmented by zeros, or negative 1, 1, 1, negative 1, 0, 0. This 2 by 2 system reduces to the following. C1 is C2, and we'll have C2 into 1 and 1. And just like before, we are going to take this basis vector to be the second eigenvector, which means the second solution is the vector 1, 1, e to the 3t. Well, now we've got a bit of a problem. What is the general solution to this system? I have two individual solutions, and both x1 of t and x2 of t satisfy this differential equation. And to show you that, remember that the differential equation here is x prime equals ax. If I were to take x2, which is the vector 1, 1, e to the 3t, the derivative of this x2 is going to give me 3, 1, 1, e to the 3t. If I were to sub this into the differential equation, what I'd have is 3, 1, 1, e to the 3t on the left side, the matrix 2, 1, 1, 2 times the vector 1, 1, e to the 3t. I'm curious as to whether or not those will be equal. Well, you can see for yourself just by matrix vector product, these are the same. So this really is a solution. So both of these things will end up satisfying the differential equation. And what ends up happening is we get a very important result because we have a linear system. If x1 and x2 both satisfy a differential equation like this, then it will turn out that any linear combination of them also solves the DE. And if you want to take a look at that, we're going to let some solution be that exact linear combination of these two solutions. The derivative of this thing would simply be the derivative of this expression above, which by linearity of the derivative is going to give me c1x1 prime plus c2x2 prime. And if I were to take the matrix vector product here, I'd have the matrix A c1x1 plus c2x2, And by linearity of the matrix vector product, I'm going to get CAX1 plus C2AX2. Since each of these things satisfies the DE, what that tells you is that X1 prime is AX1 and X2 prime is AX2. This expression right here is X1 prime. This expression right here is X2 prime. And if we take a look at the equation and we sub everything in, what we'll find is on the left, we'll have C1 X1 prime plus C2 X2 prime, and it will in fact equal C1 X1 prime plus C2 X2 prime. So it is a solution. This thing right here does in fact solve the system. And this is something that can be generalized. We won't show it. We will state it without proof. If this matrix A has n different solutions, x1 all the way down to xn, for this system x prime equals ax, then it will turn out that any linear combination of those solutions is also a solution to the DE. So back to our example, C1 x1 of t plus C2 x2 of t will solve this particular system, 2, 1, 1, 2 into x. So that means that the solution in this case is going to be 1, negative 1 e to the t plus C2, 1, 1 e to the 3t. Now, if you wanted to expand this and write it out term by term, what you will find is that y1 prime of t, y2 prime of t is c1 e to the t plus c2 e to the 3t, negative c1 e to the t plus c2 e to the 3t. Or you'll have y1, these should not be primed here. You'll have y1 of t is c1 e to the t plus c2 e to the 3t. y2 of t is negative c1 e to the t plus c2 e to the 3t. Now, the ultimate question is this the general solution? This turns out to be infinitely many solutions because of these arbitrary constants. I don't know what their value is, and in fact, any value will still allow me to satisfy the differential equation. What we're going to want to do is try to find a unique solution. And for that, we need initial conditions. And the initial conditions in our case are just going to be given by some vector of constants, alpha and some beta. It will turn out to be unique. There is a theorem that we will not prove here that will guarantee that this will provide us with a unique solution. So back to our example, if we are given that the initial conditions are 2 and 1, this means y1 of 0 is 2 and y2 of 0 is 1. We are going to apply these initial conditions. Our solution vector was c1, 1, negative 1 e to the t plus c2, 1, 1 e to the 3t, x of 0. That's c1, 1, negative 1, e to the 0, plus c2, 1, 1, e to the 0, which is going to give me c1, 1, negative 1, plus c2, 1, 1. This vector was a 2 and a 1, so what we want to do is figure out what these constants are, and that means we need to solve a regular old system of linear equations. And if this system has a unique solution, then we will in turn have a unique solution to our differential equation. This, you will see very easily, will indeed have a unique solution. If we just add the two rows together, what we'll find is the following. And if we perform one more row operation here, so what we'll find is C1 is a half and C2 is 3 halves. So the unique solution to this initial value problem, the one with the differential equation plus initial conditions, is 1 half, 1, negative 1 e to the t, and 3 halves, 1, 1 e to the 3t. If you want to think of it, these are each vectors. But if you wanted to separate it out, y1 of t would be the top entries. It would be 1 half e to the t plus 3 halves e to the 3t. And y2 of t would be negative 1 half e to the t plus 3 halves e to the 3t. Now note, in general, for some sort of n by n system, our solution is going to look like this. We'll have C1 V1 e to the lambda 1t all the way down to some Cn Vn e to the lambda nt. If we have initial conditions, x of 0 is some vector of constants, and we'll just call this alpha vector, we want to apply these initial conditions, and we want to ask if we're going to have a unique solution. We are going to have a unique solution only if we can solve x of 0 equals alpha uniquely. X of 0 is like saying take this solution, and everywhere I see an exponential term, it's going to have a 0 power. So we'll end up having C1 V1 all the way down to Cn Vn, and that's equal to alpha. So that means what we need to do is then solve this system. Because these are eigenvectors of the matrix A, we will have a unique solution only if we have n eigenvectors. That means we have an eigenvector basis for Rn, which turns out that we will have a unique solution only when A is diagonalizable. That means it has a full set of eigenvalues and eigenvectors that will allow it to create a basis of eigenvectors for Rn. So when we are in the case of having a diagonalizable matrix, we are assured that we will be able to solve any system of first-order linear DEs this way.